Okay, should I start? Okay, good. Well, before starting, just a brief introduction. Well, my name is Beatriz Mañas. I'm Business Development Manager here at IBB. I think I had the opportunity to have a video conference with some of you, but not all of you, okay? So thanks for attending this training. Here with me is Sandra Alemany. She's the head of the R&D department, anthropometry knowledge area. She's gonna lead together with Sofia and Anna the session, the training session, and nothing else. Just to feel free to interrupt or say whatever you want to say. I know that you've got the move for the just a few months, but I hope I think it was in March, February, March, yeah. And whatever you think is important for us to know or to ask, feel free, because we're here these 2 sessions to try to give you some support on it. Okay.
Sounds great.
All right.
Hello.
So Sandra is gonna lead the
Good
training.
morning, everyone. So thank you very much for attending the training. For today, the training is going to be done by Ana Ruescas. She is the responsible of our laboratory, our internal laboratory of Move4D for our main research. And also Sofia, she's senior researcher also. Both are very experts using Move4D for different projects. As Beatriz mentioned before, I'm the head of the anthropometry research team. This team was the responsible of the development of Move4D. So most of the functionalities and specifications and the way of working of Move4D has been designed in our team. For the training today, we have divided the day into 2 sessions. First, we are going to do a very quick introduction to Move4D. For sure, I hope you did some trials or studies, or you initiate the research and use of Move4D. I'm not sure you have time to work with the system. Then you can have doubts about the basic use, but yeah, I would like to remind some concepts. So maybe this is something that is more or less easy for you, but I think it's necessary to have all the people in the same page and to share at least these basic concepts. The second part related to data management and protocols maybe is also, we are going to go very quick through this part also, because it's related to the user interface and how to use and deal with the data. And the second part of the training today is going to be more hard. We are going to present which is behind the data processing, the conversion from point cloud to a 3D mesh, and how this process that is done automatically inside Move4D, but the processing is very complex. So if you understand more or less the concepts and the steps behind this processing, maybe it could be useful to take more advantage of this knowledge when you are preparing the measuring session and the protocols and so on. So this part will be the hardest one. And Ryan, you mentioned 2 topics in our exchange of email, and one of them is related to the use of another template for the processing, or how to do this. And maybe after the presentation of the processing, we can discuss more about this topic. So I think more or less it's all to start. So I'm going to give the floor to Ana Ruescas, and she's going to start. And please, if you have questions, do not hesitate to interrupt or to ask during the session, so we can be more a dynamic training.
That's good. Thank you.
Okay. Okay. Good morning. My name is Ana Rescas, and I'm in charge of the session 1 and 2. You can interrupt me in case you need, or if you have any doubts during the explanation. This first session is divided into 2 points. The introduction of the system. I will talk briefly about the main characteristics of the hardware and the Move4D software. In the next point, I will explain how to perform the calibration procedure, and I will give some technical recommendation. Let's start with the introduction. Well, you already know that Move4D is a modular system. This permits to adjust the number of sensors and their location according to the needs of the scene and the motion of the capture. The main element of Move4D hardware is the module, which incorporates an internal computer, a set of infrared devices, a color camera, and different types of connection ports. The main objective of this set of 2 infrared cameras and the infrared projector is to provide a good 3D point cloud. The additional RGB camera permits to color the point cloud and build the texture of the homologous mesh. It also incorporates a lighting subsystem to permit and enhance getting the correct color of the scene. It can record at a maximum frame rate of 90 frames per second at high resolution and up to 168 frames per second at medium resolution. The module's computers are the responsible of processing the infrared images and provide the point cloud at a frame rate of 15 frames per second. That means that a capture of 150 frames will be received in the workstation in 10 seconds. Move4D can also be synchronized with other devices and can work as master or slave. The scanning volume of a 16 module setup is 2 per 3 meters of corridor and 3 meters height, with a spatial resolution of 1 millimeter and an exposure time of 1 millisecond. It provides a point cloud of about 4 million points on average per frame. The more extended solution or designs that we provide are the medium, that is built of 12 modules. The setup, the scanning volume is 2 per 3 meters height and needs a footprint of minimum 6 per 6 meters. The large is built with 16 modules and has a scanning space of 3 per 3 meters height. And in this case, the minimum footprint will increase by 1 meter in its height. And to finish, there's a portable Move4D of 12 modules and a cylindrical scanning volume of 1.5 meters diameter and 2.5 meters height. It can be built in 2 hours in a space in a footprint of 5 per 5 meters. It was specifically conceived to be used in anthropometrical survey campaigns. Well, on the back side of the module, it can be found the next elements. I will be very quick. The switching button. Remember that you can switch or turn the modules on or off by command. In second place, the input and output connections for synchronization purposes. You can connect this trigger output and the trigger input of 2 different modules. You can synchronize the devices for the calibration in the jack port, and also here are connected the lighting subsystem. In third place, here's the lighting control module. It's attached in the middle of the module. Some port for power supply. And finally, this is the motherboard of the computer. And this Ethernet connection is for communicating the workstation. A general overview of the system is shown in this slide. Move4D software is installed here in the workstation. The green lines that are connected are for the synchronization. The trigger is traveling through the elements of the system through these connections. And the dashed lines are the connections to transmit the data from the modules to the workstation. Well, this is the synchronizing unit. This unit creates shooting pulses for all the connected devices. And permit to work all of them in the same time reference. These two ports are for external devices. This is the way that IBB recommends to synchronize external devices with the Move4D. For example, RGB cameras network. In second place, these outputs are for connecting the modules. It includes 8 outputs. But this does not mean that only 8 modules can be connected, because each module has an input for this trigger and an output. So we can connect one module with another one. They usually they are installed. There's installed one synchro cable for each pair of scanning modules to avoid possible cascading errors. And finally, the USB port is for connecting the workstation. The switch is used to manage the communication between modules and the workstation. It includes 45 Ethernet connection ports with 1 GB of capacity in each port for sending and receiving information from each scan module. There are also 2 gigabit ports of 10 gigabit ports for communication with the workstation at maximum capacity to be as quick as possible. Well, the workstation receives the raw data from all the scan modules and has to process them. The workstation needs to face large amounts of data. That's why it requires a CPU with many logical threads, and it also needs a powerful GPU to permit the visualization of all this data. Here are the characteristics of the workstation. Okay, finally, you can see here the calibration tools that are used to perform the geometric calibration of the cameras. They are equipped with 3 active markers. They emit in infrared and in color camera because we have infrared and we have RGB cameras inside the module. The one calibration the one calibration allows calibration of the intrinsic and extrinsic parameters of the cameras in each module, and the reference one defines the common coordinate system in the scanning volume. Well, in the next slides, I will talk about what Move4D software permit the user to perform. Well, Move4D, I think it's important to know that Move4D is a scanning, process, and data management software. This is the start screen and show 5 shortcuts to the main functionalities. The first one is to create a new project. The second one is to create a new subject in existing project. The next one serves to acquire a new capture to a new subject. This one is for going to the data screen that is up in the window of the interface. And the next one is permits to go to the settings screen. Well, what can be done from the data screen? Well, we can select the data collection to be shown in here. I can select the project visualization or the quick captures visualization. We will deep in this kind of structure in the next session. I can select the workstation working directory in which to store the data capture and process with this button. I can create, edit, and remove projects and subjects with the two utilities. I can process, measure, and export data in extensible formats with these utilities also. And in this screen, I can access to the subject subject screen. The setting screen shows auxiliary functionalities needed to ensure that Move4D will work optimally. There are options for the calibration, the capturing mode, switching and turning off and update the modules, the status of the modules, the visualization of the cameras in these three windows, and some additional information in the log session. When we open a subject, two additional screens appear. As you can see, subject and dynamics are open when a subject is activated. What I can do is to select a subject here in the data screen, perform a double click, and open the next window. This is the appearance of the subject screen. In this screen, it can be managed here in this side, the sociodemographic data of the subject and the list of the captures associated with him or her. The utilities to record a capture, to process, to save or close. In this side are the visualization tools, points of view, and some other kind of utilities. The visualization, the exportation of visual data as images or videos can be performed in here, and some other utilities to modify the capture. For example, to clean the raw data. For example, I can erase an object to see the static measurements of the A pose, to cut the capture station by moving these slides, or erase a process frame that is not well processed, for example. This last screen is the dynamics measure screen, and it contains a predefined list of measurements whose definition is an adaptation of those in some norms. In this screen, the dynamic measurements can be calculated in here, can be drawn on the subject, on the mesh, and can be graphic. Okay, and well, this is the first part of this session, and I'm talking about the calibration in the next slides.
Anna, are you going to show some of these elements in the software? Or it's going to be later?
It's going to be later.
Okay.
Okay. Okay. Here I had a video. I don't know if you can see this. No, I don't think so. Okay, sorry for this, but I'm this one. Okay, this is a video of the calibration procedure. We connect the wand, and then we sweep all the scanning volume. As you already know, lights of the laboratory must be switched off, turn off. Okay, and what we do is to sweep in all directions. 1, 2 direction, 3 direction, and 4 directions. Okay, what happens? Then I have to check that, and this is important, the error, sorry. Oh, sorry for this, I had a problem. Okay, the errors are around 0. This is dense, and this is all in green. This is important. After that, we will calibrate the square. This is useful for referring all the calibration of the calibration of all the modules to the same reference. Okay. Okay, so only 3 cameras are needed to perform this step. And finally, we perform the global calibration. And apply. Okay, and apply. These are the results of the alignment. In the around the diagonal, what we have to see is a green color. Okay, and once checked, we close the dialog and apply. Something that is important in these cases is to sweep the volume scanning with the one being vertical, with the spheres being vertical, because it is quicker to sweep all the volume, scaling volume with this orientation. Okay, we just applied, and that's all. Okay, let me continue with this. Okay. Okay. And what is important, some technical aspects, the one must be vertical, and then the speed must be gentle, because if we go very rapidly, then this is what the camera is watching, and probably will not provide the good center of the blob. You already know that these are the settings for the one calibration. We do usually do not modify these numbers. These are the recommended values. We first do the one calibration. As we already know, this is the sphere A, C, and B. And this is for the elevation of this sphere from the floor. This is the total number of the capture frames. We have already seen that you can control the performance of the process. This is important too, because I have already talk about this. If this is not good, if something is wrong in this window, in this dialog, you can press the recalibrate module until you get these results. Okay, and when the calibration summary is okay and is in green, you can apply the calibration. Okay, there's another functionality that is verifying the calibration. For example, I just calibrated the system, and then I'm recording in 2 hours something. I can verify the calibration that I did yesterday. So I check that everything is fine. I don't have to complete the whole calibration procedure. Well, this is the end of the first session. I don't know if you have any question, but if not, I'm showing you in live the. Well,
Yeah, I would like to ask the team from the university if did you have some troubles with the calibration? Are you agile with the calibration, or did you have some feedback about this?
Every time we've calibrated, it went pretty smoothly.
Yeah. Maybe you have also experience with mock-up systems, and the calibration is quite similar with compared to the mock-ups.
Yeah, we have a markered system, and it's with the wand as well, so we're used to sweeping the area.
Okay. Regarding the synchronization, Anna explains the different options. I would like to mention that in our laboratory, we have experience synchronizing different type of biomechanical devices. So we did measurements synchronizing force plates. We did project synchronizing OptiTrack motion capture system, and now we are running a project including RGB cameras, thermal cameras. Thermal cameras are quite difficult because one thing is to synchronize and to measure at the same time, and the other thing is to calibrate in the same reference systems in order to project the image of the thermal camera in the mesh. So this is something that we are working on it now. We have some experience, and just in case in the future you have interest. And also the photocells that sometimes are interesting to synchronize it in order to start the measurements driven by the photocell. This is also additional tools. Anna, I'm not sure if I'm covering all.
No, it's fine.
Okay.
We also
Absolutely.
we also already synchronized Vicon, the optical cameras, the video cameras, and the force plates. So Danielle was able to help us. We've collected some trials synchronously, and everything seems to be working. And then outside the software, we aligned the coordinate systems from 4D and Vicon as well. So we've made some good progress.
Okay, good. I cannot hear you very well, but more or less, I think I understood.
I can repeat it. So we already have synchronized Move 4D with our Vicon system, which has markered and markerless cameras and force plates with Daniel's help. So we're able to collect using all four systems at once and synchronously, and we align our coordinate systems outside of the software.
Okay, that's super nice. Yeah, you're very advanced then on this. Okay, good.
Well, I continue. I'm sharing with you the interface of the Move4D. I'm here in the Human Analysis Lab in the laboratory, and well, I will try to explain more or less how we do our projects, and if it's something that you need or you can suggest, or if you think it's a good idea or something, please interrupt me. When we start Move4D, we see this window, and I do usually go to the settings, because what we first do is to verify that the calibration is fine. I'm doing this. It's 1 minute, less than 1 minute to have these results. Okay, the verification it's completed and it's correct. So what I do is to be sure that what I'm recording is in the best state as we can capture. Okay. Then something that is important for us is to verify that the clothing that we are using in our projects is not giving us any problem. So let me show you something. Okay, as you can see, these two garments are black. Okay, but when we see here in these cameras, in the infrared cameras, the appearance, what we see is that in the upper garment there exists a contrast between the projection of the infrared projector and the background of the garment, but this one has a very little contrast. So we will discard this garment for our projects. A tip that we can give you is to check before you do something. If you don't know how what is the behavior of a special garment or a specific garment, you can check in this settings window. Okay. Can you hear me?
Yeah.
Okay, fine. Well, something that is important too when we planify, when we plan a project is to know that in the project we use a protocol of measurements, and we can define it before. Where we can define this? Here in the settings mode. Some predefined modes are a pose. This is mandatory for all the captures. If you want to process with a homologous mesh, gate and jump, but you can define a new one. This is the name. In the description, you can introduce something that you need, the instructions to give to the subject, and here are the technical settings of the capture mode. For example, I want to get, for example, 10 seconds of a movement. The way that we introduce these 10 seconds is to first define the frequency, the frames per second, and then multiply this frequency by the number of seconds that you want to record. In this case, 10 per 10 is 100. Then the resolution, we do usually always work at high resolution, but you can select also medium resolution. The type of synchronization, as told before, we can define Move4D as master or slave. Internal means that Move4D is working as master. External synchro means that Move4D is working as a slave. An external trigger is when we start recording when an external device gives us a trigger, for example, a photocell. We do usually use the visible lights on. Otherwise, the quality of the texture will be not as good as it can. And a countdown, if you want to record it, start the recording later. Okay, then I can define this. And what the next that we will do is to create a new project. We go to the data screen and we can do the open or create a new project with these options. This is for describing whatever you need to describe the prefix of the name of the subject. For example, if I start by new project, all the labels of the subjects will start with NPR. Later, it is configured by a number. This is the first subject. This will be the first subject of my project. And this is for defining the gender, in this case, male. I can also give some more information about if he's diabetic, because perhaps it is of my interest or for my project. And in this protocol, I can add all the captures mode that I will need to complete my project. Okay. I have already defined a new project, and now I'm defining a new subject. What is mandatory is to introduce the date of birth, at least the year, and the gender. Okay. What can we do to start the recording in this context, in a project? We use the wizard, because in this window, I can start the capture of the A pose that, if you remember, it's mandatory. And I can navigate through the protocol, and automatically the captures in the protocol will appear, and I will be able to capture them. Okay. Another way of using the data is to go to the environment of quick captures. Here, what we have is some folders with the month and year where the capture was done. In this case, I have already prepared this example, and I open the subject, and I can see some captures that I have already done. Which is the difference between quick captures and protocols? Is that when I use the quick capture subjects, I have to configure each of the captures that I'm doing during the session, like this. Okay. This is not a person, but what I want you to see is that it is capturing, and now when it's receiving, we can preview the reception of the point cloud in this moment, and we have the chance to cancel the reception if we see that is something that is not good, that it's something wrong with it. Okay. If there is something you are interested in, more interested in, or if you want me to explain something in detail, please interrupt me, and there's no problem. Okay. This environment is for processing. What is interesting in here, that I can process the whole, okay, I can process the whole project. Then I go here, I select all the subjects, all the captures I need, and start. Then I go home, and when I come back to work, I will have all the processes done. But I can also do it by subject. With this one, I can compute the dynamic measurements of the subject or the project. And I can also export the data in exchangeable formats of all the project or just the subject. Okay. What about this? Do you know what means this? This is for checking that the capture has been already done. This is for referring that this has been processed with a non-homologous mesh. This is the symbol for the homologous mesh process. And well, I will start with this one because now what I want to do is to let you know the capabilities for managing the raw data. For example, in these cases, I am using the utility to cut all the information that is not complete. For example, from here to here, with this utility, with the scissors, I can crop the capture. Then what I have to do is to save, and that's all. Another utility for modifying the capture is to remove, for example, here. Sorry. For example, in here, if I want to remove something that has not worked properly, the process has failed, I have the possibility to do it with the software of Move4D. It's opening the raw scan. This is the more hard. Okay, and then the processed. Okay, for example, sorry. Okay, in the left side of the window, I can see the raw point cloud. And in this right side, I can see the homologous mesh with the option of being colored, with no color, with black borders. Here in the mode, you have a lot of possibilities. This is very informative because this way you can see where the joints are located inside the homologous mesh. And well, for example, if something failed in here, what I can do is to remove this mesh, this frame mesh. And then I have the possibility to recompute this isolated frame. Where I can do that in processing. Okay, sorry. In the processing, I have the possibility to reprocess the whole capture, or just the frames, to reprocess the whole capture, or just the frames that has no mesh. Okay, some other utilities that are interesting is the clean utility. For example, in this, capture, the chair was mandatory because of the movement and the posture, and that was needed for fitting. Okay. Well, With this utility, what we can do is to select or at the points that I don't want to be in the scene and erase. This is done frame by frame. Okay. And then, okay. This has to be done frame by frame. Okay, but in newer versions of the Move 4D, it can be done automatically for all the frames. Okay. I have already talked about the the options to see in here the raw scan, and I can see in another window for example, sorry, the homologous mesh. Okay. Okay. This is plenty of possibilities here to configure your own or your preferred visualization. I do usually synchronize two views of the raw scan. This is the raw scan, and this other is for the homologous mesh. I use this one for synchronizing them. For me, it's very helpful in order to check if everything has been gone well or not. Here is the possibilities to see a color or other characteristic of the data. Here you can select the projections, can be orthogonal, orthographic, or perspective. The number of views, you can select also a different number of views. Some views. You can change also the background, and you can select 4 different colors. Also, you can see some elements. For example, you can hide the floor, and here I prefer to know where's the scanning volume, and in this last one, I am seeing where the modules are set. Okay. The measurements are for the A pose. I will later see this, and this is for doing a view that you can use in a presentation. For example, you can save also this. You can also save this PNG with these options. With the same colors are seen in the screen, or with alpha channel. For example, this one. I can save this picture, and also I can perform also a video. We'll start saving the video. You can see what is recording to have additional documentation of your project or presentation or whatever. Okay. Later we will see the measurements that you can compute with the software, because there's a distinction between the normative measurements in the static A pose that is mandatory, and other dynamic measurements that are provided with the software. Okay. Okay, so in this case, in this window, because the homologous mesh is open, I can access the dynamics window. In here, we have a collection of measurements that I can compute. For example, these first two. It's very quick to compute, and then we can export the dynamic measurements and to have detailed information about something that hasn't been able to measure before. In the newer version, we will provide an interface to design custom measurements. But this is in the near future. Okay, this is a long capture, but it's done in 2 minutes. What we do is to check the measurement that we have already computed, and we can see on the mesh. And also we can represent them here. And we will have a look of the kind of measurements and the elongation and contraction of the muscles by monitoring the contours or the length of the measurement. This is how it works. In the data, what you can do is to you can export this data also. And well, if I haven't seen this, just to say that you can isolate the point cloud of each module. Okay, this is done in this window in this side of the dialog, the move for the dialog, and well, and that's all. And I think this is just the last point I'm explaining. Is about the measurements in the A pose. This is a collection of more or less 100 measurements that are described here, and the normative is also detailed, and you can see the height, and you can also, oh, sorry, I don't know why this is not working. Oh, yes, I know, because I have to be in here in the homologous mesh visualization. You can see, well, a huge collection of measurements, a lot of information of the subjects, and you can export this data and well, do a lot of stuff in here. I don't know if it's something left or if you are interested in something else about the management of Move4D. But well, I think I'm finished with this.
Okay, I would like to point out two comments from Anna. One is related to the how to delete the objects, because the automatic processing of the captures should be done in a specific conditions. So the subjects with tight clothing and without objects. But sometimes it's necessary to measure with objects, with a racket, a bike, a seat or something. So at this moment, it's necessary to do this, to delete the object manually. This is very time consuming. We are preparing a tool to delete the object automatically. And it should be robust, or more or less robust, and it should be also applicable to objects that are in a static way, like in a bike, a static bike, or a seat, and also with objects that will be in movement, like a ball or a racket that will be moving around. This is one element, and the other is related to the body measurements. So to be only strict in the list of measurements that we are providing, the list of automatic measurements in a pose or the short list in dynamic, it's limited, especially for some specific research that requires additional measurements. It's possible to do this outside Move4D, taking advantage of the homologous mesh and using the vertex of the mesh as reference points to program, maybe in Python, our own measurements. But what we are doing, it's working in a interface inside Move4D to define personalized measurements. So this is something that is going to come also with the new version. And
Okay.
yeah, and now we are going to present the data processing. Sofia is going to.
Hello. Okay, so yes, let me share my screen. Okay. I think you are already seeing my screen, that's right? Okay,
Yeah.
so yes, I'm going to move to the third part of the third session of today. And as Sandra mentioned at the beginning, this can be more dense because it's more theoretical. But we thought it was really important for you to know what is behind this processing process, because to understand how the homologous mesh is built, it can give you potential to your research and also to develop different connections or exports and so on. So, but at the end, I'm going to do an overview because this is maybe too much information for 1 hour. So I'm going to do an overview, but we have a paper published with all the details about the processing. So we're going to share, well, this session record for sure, and then also the paper. So I'm sure you will be, will have, in case you need it, a more detailed version. But of course, if you have any question, you can ask me, and me or any of the people here present, we will try to answer. And if not, we will share your question to the people that are more in charge of developing these algorithms. Okay, so yeah, let's go to the mesh processing methodology. So, which is our objective? Well, as you know, one thing is what we capture, and the other thing is how we can use this information captured by the system. So what we need to do is to create an automatic pipeline to go from the real human in motion that we have captured with the optic system to a digital twin that can be treated and also export in to different third-party softwares. So we will start from a person performing a motion, a person which will have a specific size, a specific shape, and will move in a specific way. We will capture this and collect a point cloud, a raw point cloud, and we will do a processing to get a homologous mesh with an internal skeleton and with a structure organized and with anatomical meaning to export it. Well, not necessary to export it, but to be able to be exported in case we need, with an internal skeleton, and with the concept of homology that we will review in the next slides. The mesh we're using is a one which has 50,000 vertices, and it has anatomical correspondence between subjects and also along the sequence. We will see this in detail. So what we have once we capture? If you have performed already some captures, you probably are familiar with this observation, but we will have a really, really dense point cloud composed of millions of points. As we can see here in the detail, we have a lot of density, and this point cloud is noisy because it also captures some noise. It's not a perfect surface, it has some noise, and also it's unstructured because each point of these clouds doesn't have anatomical meaning or any kind of correspondence. And also these clouds will have some holes because there are some parts like the armpits or the crotch that are not visible by the modules. And here we will have some occlusions, or for instance, in this example that we are seeing, we can see that part of the inner arm, we have an occlusion because the modules are not able to see this. So this is what we have, and what we want to have is a complete mesh. So what the characteristics of the homologous mesh will be: one, it has to be lightweight, because here, when we are managing this point cloud, we have millions of points and the files are really heavy. So we wanted to convert these to a lightweight one, to be also single surface, watertight, so with no holes, yes, complete, and structure. Also, this homologous mesh will include an internal skeleton. So not only the points, the vertex on the surface will have some meaning, but also we will have an internal structure that will make it compatible with other third-party softwares, like the ones working on animation applications, among other. So, and more important, we want this to be automatic, because I don't know if you're familiar with other kind of scans and processing, but other scans normally need some guidance to get from the raw point cloud to the final mesh, because you need some key points to guide the process. But this is really time consuming, and it is not feasible to do when you have a capture of hundreds of frames. And the value of our processing is that there is no manual intervention and is completely automatic. Okay, so one of the objectives of the processing, make it complete and watertight. We can see, I wanted to show you some examples that you will find in your use and your experience with the Move 4D. And there, naturally, some postures will present some holes. Like in this example, we can see that in the chest, we have some occlusions. And once we do the processing, we will have all this information covered by the models that work behind and that we will review in the following slides. Also, we have some other circumstances, like when we are capturing kids, they are smaller than the adults, and the position of the models are not optimized for these sizes. They are generally optimized for an adult shape. So besides the occlusion, the normal occlusions of that an adult will have, maybe we can have some more in the case of the kids. But the processing methodology will be able to solve these holes and occlusions in the kids, and will also be able to have a watertight complete mesh, homologous mesh. Of course, if you in your experience, you will see, it depends on the postures that you capture, but we were performing projects about sport positions. And here we have an example of a male performing a plank. And of course, we have a lot of surface in the abdomen area that is horizontal and really close to the floor. And here we have a lot of information missing, but the processing is able to, with some guidance, not manual guidance, but being able to see the face and other factors that the processing needs, it is able to reconstruct the whole body. Also, in the example that Anna and Sandra were talking about of the objects, which is really common to need to scan this way, there will be some occlusions, like in the case of the bike, the seat area, or just using a seat, we were going to not be able to have these points available because they are overlap with the objects. And when we are deleting the object, we have a clean point cloud, but we will have an additional holes there. But at the same time, we're going to be able to solve these gaps of information. Okay, so the next objective of the processing is to create a structure. So here in this small video, we can see that in 6 different scans of real people with really different body shapes, if we click on one vertex of the homologous mesh, it is corresponded to all the subjects. So there is anatomical correspondence, because this is the concept of homology, that there is a structure with anatomical correspondency. So I don't know why this stopped, but okay. So in the case of an A pose, a static pose, we will have anatomical correspondence along all the subjects, but also, since this is a dynamic scanner, we also need it during the motion. And this is the other property of the homology, that also along the sequence, I will be able to track the vertex with this anatomical correspondence. So the tip of the nose, the nose, or the position of the nipples will be the same along the sequence, and also between the subjects. This is really interesting and like essential, because when you are doing the research and you want to track the landmarks to follow biomechanical motion, or different between shapes performing under different circumstances or whatever, you need to ensure that you're tracking a point that you control. So this was another of the requirements of this fitting, because it's essential for the research to have this. Okay, so this is the needs, the things we need to have, and then how we do that. So the methodology that Move4D follows is called the template fitting. Okay, so here in this small video, we can see like an overview on how this fitting looks. And here in the right, let me see if this works. No. Okay, we have the raw point cloud. We can see that it's a raw point cloud because it has holes, there has some noise. And okay, here we have the template. We have a template for males, females, and another different for children. So because there are some like really relevant differences. So the Move4D uses different templates in these 3 cases. So we part from this template. So the template fitting objective is to deform this template to reproduce in a really accurate way the surface of the capture point cloud. This is going to be a process, an iterative process, and it has different stages, and we will kind of overview all this, but we can see now here that it is scaled in size and in pose, and also the deformation will be adjust to minimize the difference in distance between the surface of the captured and the surface of the final mesh. So as we said, in other processes, they use some key points to guide this fitting, because you need to ensure that the deformation is performed with anatomical meaning. And so this process, this key point, this guidance is also performed in the Move4D process, but it's completely automatic as I mentioned. Okay, so we need to, just to summarize, we need to do this template fitting which we have seen in the previous slide, but not only in the A pose, but in every pose. To get the homology without any reference point, because we're not going to have any manual intervention, and also with temporal consistency. This means that since we are going to process frame by frame during a motion, there is a lot of relationship between frames, because this is a motion, a real motion performed by a human. So the difference between frames, it has to be really small, because the real motion happen in a soft way. So this is something that the processing also has to take into account. And also we need to be really accurate, because the difference between our calculated mesh has to reproduce in the most accurate way the things we captured in the lab, because that's the point of everything. Okay, and everything automatic. For doing this objective, to get these objectives, we use a human body model that will guide this template fitting to avoid inconsistencies or that really strange or uncontrolled fits happen. So this human body is the basis of all this process, and I'm going to introduce it in the next slide. So for understanding more or less this human model, it is important to talk about the shape model and the pose model, because one thing is the shapes of a body, and the other is which is the posture that is adopting. But these two concepts cannot be treated independently, because the pose influences the shape of a 3D body, because when you can have one shape in static, and when you are moving, there are some deformation that are associated to that pose. Let's say, for instance, some muscle activations and things like that, or deformations of the soft tissue that it will be necessary to control. So at the end, the model will be a combination of shape model and pose model. So what about the shape model that Move4D is using. The shape model, the basis of the shape model is created from the database of 3D bodies. Here we have a collection of 12,000 bodies, and they were collected, real people collected from Spain, but also from the US, and also there's some proportion of people from Asia. So with this database, we have a sample that is representing the variability of shape and size along the human population. So here with this database, we first need to have all these meshes standardized and aligned to remove all the variability that has not to do with the shape variability, like rotations or translations and poses, strange poses. And now we have all these, a principal component analysis is performed. With this analysis, the objective is to describe in parameters the variability of shape and size in the human body. So the model is created with 100 parameter components that describe different parts of the variability. For instance, the first component is describing the size of a person. The second is more related to the body mass index. And we can see here some examples. For instance, this has to do with the proportions of trunk, arms, and so on. And this fourth component is more related to like the general posture of body when it's in a rest pose, and so on. So this is a set of 100 parameters that are describing the different variations that makes each body different. So here with this model, we can create, we can describing parameters a body, and we also can create different one. We can see here an example of some that are real and the others have been created moving the values of these parameters. Of course, this model is not going to be able to describe with detail any person in the world, because we at the end have some details that made us unique. But this is going to be like the core, the fundamentals, and these small details will be then in other processes, in the other stages of the processing will be completed and obtained. But this needs to be like the fundamentals, because the more robust or better is your initial guess of the mesh, will be better to refine the approximation to get the most accurate and robust final mesh. Okay, and then we go to the second concept, which is the pose model. The pose model is really related to the internal skeleton of that is inside of the homologous mesh, and the pose model will be a combination of angles of the joints that conform this skeleton. We are using for this, like fundamentally, the linear blend skinning. Okay, that it means that 3D in another pose is just a blending of 3D in the rest pose. But of course, this linear blend skinning has some limitations, because at the end, as the name says, it's just a blending, and it is not including a real soft tissue deformation considerations. So we will have some limitations, like here we can see an artifact because this is not really realistic. Or for instance, as I was saying before, the activation of the muscles are not observed in the linear blend skinning. But in the algorithm of the Move4D, this has been improved and refined because with training with a big set of different poses of different subjects, we also will include an additional term to the fitting that will take into account these kind of deformations that are really related to the pose. Like for instance, when you blend, you flexion your elbow or other parts of the body. So this way, as I said before, we will go to a closer first guess. So it will minimize the distance between the surface that I want to get close to and my initial guess. Because if we start from here, we have like a lot of information missing, and here when the template is fitting the scanned raw point cloud, we can have here some results that are not the desired. So with this additional soft tissue deformation term, we can go and start with a best initial guess. Okay, so let me show you the formula of the model, like an overview, and the body models that the processing is using. So first of all, we use the body shape and pose model, which is this one. Okay, so this term here is the shape term. And this is the one that I was telling you before that was learned from 12,000 users in the A pose. Then in the shape model, we also are introducing a soft tissue component that was learned from 24,000 poses of 11 subjects that were performing a variety of poses that was covering more or less the typical motion of a human body performing different exercises. So having this shape model with this extra component, we build the complete model, which is the structure of the linear blend skinning model with this term, and then considering also the joints that are here, okay, because, sorry, I wanted to explain this before, but this is the look and the structure of the template mesh that we are using with our model. And this is a 50,000 birds mesh. And this is the structure of the skeleton. We have 23 joints and without the hands, and we go to 52 joints when we include the hands. So the model will also include this term related to the joints and also the angles of the joints. But these angles will not be any collection of angles because we wanted to make it more robust, and these angles work after a PCA that constricts some not possible anatomical position. Okay, what means? I wanted to clarify this because I don't know if I was clear enough. We know that we are treating with human bodies, and we already know some information on how the body model moves and what it is possible to do. So these are the angles of the joints, but taking into account that which are the feasible postures for a human body. And then we also have another term, which is related to the skin attachments, which relate the joints with the vertex closer to it. So which vertex are moving or related to the motion of the joints. Okay, this is an overview. I'm sure you will be able to find deeper details in the paper, but please feel free to ask whatever you want. Okay, this is the shape. Sorry, the body shape and pose. Then we also have 3 more models, but they are subsets of the global mesh. And one is the second is for the hand shape and pose, because first we had a version without hands. It was in a fist, but then we included the hand in our mesh, and we trained this the model of the hand with a database called Mano of 2,000 hands to create the model, and it is really similar to the body, but in the case of the hand. Then we have a third model, which is kind of the connection of the hand and the body, and also for reducing the dimensionality, because we know there are some hand motions that are not going to happen, and we cannot permit those. And this model, which does is to connect the hand with the body and to reduce these dimensions that we don't want to give freedom to. And the rest is, and the last is the model related to the face, because in the face we have a different circumstance, because the emotions in the face are not related to any joint, but they are a characteristic really important of the possibilities of the face expressions. And for that, like a additional model was trained with a basal face model that was in charge of tracking the the um, the the fitting in the face to ensure that the shapes and the expressions are corresponded to human normal shape and expressions. And also, I also included here the picture of the texture, because the texture is also, it has also homology. It's not just a print without meaning, but the center of the eye in the texture has to be printed over the center of the eye in the vertex of our mesh. Okay, so the model serves as the structure and the skeleton of the registration, but then we have to proceed to get to the form and align our mesh to the final one. So the general objective of the registration is to calculate some components that will describe the uniqueness of each homologous mesh representing one person in a pose or in different poses. So we have on the one hand some shape parameters like scaling factor, bones scaling factor, the size of the or the distance between joints, if you want to see it like that. Then we have the shape components of the body model that we reviewed before. And then here, the epsilon is a really relevant factor, which is all these small deformations that are not described by the model, but exist in the real life, different for each person. So this is a component that needs to be calculated during the process. And then in the pose parameters, we have the pose components, the angles that we have seen that also are restricted by physiological limitations, and the deformations that are related to each pose. So the difference of the model gaze and the difference, the final difference that completes the mesh to be accurate and similar to the capture. And as you know, you need first to capture the A pose and to compute the A pose, and then you can use you can process any other sequence. But for a subject, you always have to start with the A pose, and this is because there are some parameters that are only computed once in the A pose, because it was more complex and time consuming. So this is why it was divided in two. You first do a short capture in the A pose, you compute it, and you compute there the shape and pose parameters. It's just once per subject. And then in another step, you can compute any motion sequence, and the shape parameters are obtained and fixed from the previous A pose process. And then only the pose parameters are computed. And in both steps, these two steps, we have 4 small steps inside, which are the landmarking, the initial alignment, the optimization, and the texture. Okay, so in summary, I have my gold standard, my objective, my capture, which is here, Y, and I have then the shape the shape model, sorry, the shape model with the component of the, you can see here, for instance, that there are some details that are obtained through this extra element. And then we have the pose model that takes into account, of course, the shape model, and the pose model with the deformation that are characteristic from each frame. And this is what we need to calculate from here to here. Okay, so as I said, there is 4 steps: landmarking, initial alignment, optimization, and then the texture. So let's start with the landmarking. The landmarking is different for the A pose and for the rest of the sequences. In the A pose, we use a deep learning network, which is PointNet++, which is trained with a set of A poses, and the objective here is to classify the points of the point cloud with the vertex of our homologous mesh. So the landmarking offers a first classification of our point cloud. Since we need to have more detail and accuracy in the case of the hand and the face, because they are like more special and they have to be treated in a special way. Additionally to the classification of the landmark of the point, sorry, we use the color cameras of the Mu4D to, with the MediaPipe library, detect some position of a set of landmarks to have also a classification to start the process. I was saying that this is different in the A pose than in the motion sequence because for now we don't have this network for its position. It is only in the A pose, because, well, we maybe will be able to have it in the future, but also this is really time consuming, but it will be seen in the future. So what we do is something a different approach. what is done is to with the virtual camera of the scan, we take 3 point of views of the point cloud. So with the media pipe library, it detects the position of the joints. So here, the landmarks that we are tracking are joints in the motion. And since we have 3 perspective, then we are able to build a 3D, the positions of the joints in 3D. But since the face, as I said, is really peculiar and important, the process of the identification of the landmarks in the face and in the hands is performed in each frame. Okay, so after the landmarking, we go to the initial alignment. What is the objective of this? So we need to calculate a first a guess of our of the mesh. I mean, the objective is to find the angles and the global translation of the mesh to place it in the position that the capture is. So in this initial alignment, the shape parameters are fixed because our objective is to find like the angles and the translation. So we need to move our template in a pose or whatever to the exact position of the capture point cloud. So as I said, we are fixing the parameters to 0, and then in the A pose, and then in the sequence, we're going to just use these parameters from the A pose because it has been done in advance. So during this process, what for guessing this, we're just minimizing some objective functions. So on the one hand, we have a landmark that is going to penalize landmark distances because we want to get the closest we can to the landmarks that are following, are guiding, sorry, our process. And the other term is going to check that the temporal consistency is maintained. Because as I said, we need to have these soft motions. So the penalization of the landmark distances are performed in 3 phases. The first has to do with the pose parameters in the predominant pose models that I said in the that are feasible for a human body. Then it also includes the hands and optimize those angles. And the third part is to say, sorry, this is the first, the second, and the third replaces the body landmarks by a term that calculates the distance between the scan vertices and a set of scan vertices and the nearest model vertices. So, because what we want to do is to minimize the distance between the point cloud surface and the mesh. Okay, so yeah, we move from the initial alignment. We have the template located in the posture and that fits better with the landmarks that are guiding our process. And then we need to finish the processing with the optimization. So in the optimization, we just need to find all the parameters that I introduced before, the epsilons, the F and S, which is the deformation. And in the A pose, all the parameters are optimized, and then in the sequence, only the ones related to the pose and also the face expressions. Okay, so for getting this is an iterative process. There is a series of objective functions that will guide my the fitting to get to the final one. So the most important one, the first, penalizes the distance between the scan and the model. Then the second one ensures that, enforces that there is a body smoothness, because it needs to characterize um, a normal human shape, and this way we can avoid some edges and some shapes that are not wanted and possible. Then we have shape method. Okay. Okay, so this since we need to have control of the process, this third part tries to give more importance to the angles that are described by the model, and try to make it small, the variation in each frame, because of course we will always need some component here to finish the formation, but when we give more importance to the model, we kind of control better the process. Then we have here two other equations related to the phase landmarks to ensure that the phase is the mesh in the phase area is deformed in a correct way. Okay, so this way, this is at the end of this process, we will have a final result of our homologous mesh. Here in this video, I wanted to show you an example, because I was talking about before the temporal consistency. Without this term, we can see here we have some small jumps, because if you, sorry, here, you can see here that this is like vibrating, because if you calculate the frames separately, you cannot ensure that the motion is a complete sequence, but not independent. Okay, so at the end of this, we have being able to create the homologous mesh processing. And let me talk about the time that it takes. Probably you have already been using it, and the estimated time per second is 13 seconds, and this is quite efficient. Is comparing with other systems, this is an algorithm that is really efficient and really optimized. But of course, normally what we do, how we proceed in the lab, is to capture the apose, process the apose, because we need to check, since it will guide the shape of the rest of the capture. It is important to check that everything is okay, and then the rest of the capture we normally process everything during the night, because at the end, if you have long sequence, it is better to just check that the point cloud looks fine, the apose is fine, and then you can perform this processing during the night. Okay, so here there is an example of the accuracy, and in general, the accuracy is around 1 millimeter, and we can see, well, as expected, probably we can see in the most particular parts, like the hands, which are really complex and with small details, we have the bigger differences, and also, of course, in the parts that were occluded and we have a hole. But in general, we can see many parts which, when we have almost zero, a zero of difference between scan and mesh. And another thing that I wanted to talk about, and I think I'm quite almost finishing, I think, is the export formats, because one thing is how the processing calculates and structures the information to at the end define a deformation that describes well the scanning. But there are some other softwares that are not compatible with this structure. So to be able to export, we had to rebuild a little bit the structure, but at the end it has then again all the information. And instead of having a change, an epsilon for this epsilon S and epsilon F, we have to insert all this information in a term which is called blend shape. So here we can see the scan without this blend shape, and I don't know if you can see with detail, but let me, well, maybe here, but this is not the most the most critical part. But here in the elbows, there were you could see some of the artifacts that I showed at the beginning, and this is the capture, the homologous mesh, including this deformation. Sorry, because I want to play this again. Okay, now here, we have here some artifacts, and here we have a better, more realistic deformation. And here, just to visualize, we have the rest pose or the A pose, and this term is added to for you to see how much the real soft tissue deformation differs from the normal linear blend skinning. So you can see here all the deformations that the human body suffers or gets along a normal motion. Okay. Okay, so yeah, I just needed to introduce one more concept, and that will be all. Here we have some examples because we have performed different projects and created different databases. Here, these are some examples of a project of sports, and the subject had to perform a series of sport motions. I don't know why this goes a little bit small, but here, yeah, I just wanted to show some examples. Then, yeah, there are some considerations for the homologous processing because it gives you a lot, but you need to accomplish some requirements that are really important. I'm sure you already know, or in the training that Danny performed, but it is basic to have tight clothing because you are trying to characterize the body shapes. Also, you need to have short hair or tied up hair, or to use a cap because the hair is not visible by the modules. Then you need to stay inside the area, no objects to process. Of course, you can capture with objects, but you have to do a step of erasing the objects and then you can process. And no multi-person, or you can capture multi-person. Well, no, because you will have occlusions, but at the end, to process, you have to delete one person or the objects to have one person without the occlusions, all the ones that you can get. I mean, you will get some occlusions, but the least occlusions you can get to perform the processing. Yeah, we see Anna explained this before, that you can clean the objects. And then to finish, I wanted to introduce the non-homologous processing, that it is also available in the software. That you may want to have this kind of processings because this has some limitations, but also has another advantages. So, which are the limitations of these non-homologous processing meshes? So it is the information is not organized. Also, won't be watertight because the holes will not be completed. It's not homologous. And the texture also won't have any correspondence, but you will not have any restrictions to capture. So it would look something like this. That's for different applications. You may be happy with this, because at the end you will also obtain like a lightweight format that represents your capture, but without all the benefits of a homologous mesh. For instance, here we have different examples, like in moving objects, or playing with objects like a ball, or different circumstances that you can think about. Okay, so I think I'm finished, because concerning where to process and explain, so from my part, I will stop sharing, but of course we can open now a round of questions or whatever. Okay.
Yeah, I guess, well, maybe you can ask. So like, we said this before, like one of our use cases obviously is maybe track soldiers with like a vest or a backpack or those types of things. So we know we can collect some movements to get their homologous mesh when they're not wearing anything, and then collect those trials again when they're moving, and maybe clean up the data using the non-homologous techniques. But I guess long-term, Allison's in the room, she created some shape models of our soldiers with backpacks and vests with no correspondence, but we're just wondering, long-term, if you have any vision for having different templates or ways that we could approach that. If that makes sense.
Yes, one of the requests of or discussion with some clients, it's related to the topology of the mesh, or even with the structure of the internal skeleton. So we did a test or a feasibility study to develop generalized methodology to convert the sequence of the capture to another topology and even to another internal skeleton. So this is something that should be customized for each specific situation. And we are thinking in providing this conversion through a plugin or a middleware, something that initially is going to work outside Move4D, because otherwise we are worried about the huge amount of possibilities that we can include if we are adding different templates. And we also understand that some of them are going to be proprietary of the client. So at least in a short, medium term, and to start, we are going to provide a plugin to do the conversion automatically. This is something that requires a small project to do the development of this conversion, and to test it in order to be sure that this is robust enough.
Yeah, because that sounds great. Like, we work with all the Canadian military, the US, the Dutch, a bunch of people. I think a lot of us have these same goals, I guess, long term, but it's not an easy thing. And we didn't know if, like, we can also collect other data in our lab with like markerless motion capture to get the underlying skeletons while we have the meshes or other things. So not sure if there's data we could share that would help test these things out or do something else. But I guess we're open to suggestions or collaborations or these types of things moving forward as well?
Yeah, sure. This is something that we can discuss in details. Maybe we can draft a short document with some specifications of in terms of interoperability with other models that are already in the market, commercial or free, or some of them that are, yeah, maybe your internal models because they are the best configurations that are going to fit the research or the studies that you are doing. So maybe drafting a small document with the specifications of interoperability will be a starting point to see which could be the options and the timeline of adapting the output to this to your requirements.
Sure, and maybe even in the short term, we can share some slides or some stuff about what we've worked on or how we looked at these before we got this system, and then maybe that will help us find forward.
Yeah, that's I think that is workable, and I can see a shorter timeline with the homologous mesh with tight clothing. Then with in the case of clothing, we are discussing internally different options to approach, because to maintain the homology, at least the anatomical homology, when in the case of soldiers, when they are wearing a lot of personal protective equipment and many layers of equipment, it's difficult. So we are losing totally the anatomy inside, covered by this kind of layer. So we have only the face, and even with the helmet, sometimes we have not the face. So anatomical homology, I can see difficult to maintain. We can scan outside and to have a closed mesh, we can force the homologous processing to do the processing of a soldier, even knowing that we haven't got homology there, with the objective of obtaining a closed mesh without holes and without the artifacts of the non-homologous mesh. And then the question is how to relate this with an internal shape if we want to understand the gaps between the different layers. And then in that case, we have different approaches possible. And even we have the option of, if we have all the equipment in digital, we have the option to dress the body. This is something that, at least for the clothing industry, we are checking the accuracy of dressing the body with cloth 3D and trying to scan the same and comparing which are the differences. So maybe the line of dressing the body with cloth 3D in the case of pattern making processes. And then we have another situation that is the animation industry, that they are not going to be precise in terms of fit, but they want to be visually beautiful. And then in that case, they are using Marvelous Design. It's a company, it's from the same company of Cloth 3D. Marvelous Design, that it's a software of dressing humans that is more addressed to animation. So more or less, the pipeline of working with dressing humans in clothing and in animation, dressing the
That sounds good. Like maybe we can even pull together, like I said, a presentation of all the different steps that we've done with having digital models of what they're wearing and putting them on virtual soldiers and collecting their data in the lab. Maybe if we provide a bit more information about use cases, that might help your team think about some of these approaches or next steps as well. Yeah. We can do that separate from this training, just to give a bit more information as well. Yeah, sure. Thank you. Yeah, we think that if we can take advantage in that kind of research of our shape and pose model, and the possibility of introducing a special soft tissue deformation for each specific subject, so we can use this model to do an inference of the internal shape of the body when we are scanning with all the equipment. So we can scan with all the equipment and then try to fit inside the body of the subject. If we use a sequence of movements of these subjects just to train and to obtain the specific pose and shape parameters of that person, and then to use it to establish this model fitted inside the equipment. This is something that, because the model that Sofia presented is something that we are using inside Move4D to do the processing. But at this moment, we are not using the model outside Move4D for this kind of research. But we know that we have this information, and maybe it's time to take advantage of these possibilities.
Yes, sounds great. I have some thoughts, so we'll pull together some of what we can do and what we have done to maybe guide our next discussion.
Okay, good. So it's 6 o'clock. We finished for today the training. Tomorrow we have 2 more sessions. I'm going to talk about the potential applications. Just I will show some of the projects that we are doing here at the IBB in order to give you ideas or possibilities of applications with the scanners. And we will finish also the part of exporting. As Sofia mentioned before, we need to rearrange the structure of the information that we are computing in the processing in order to create the different type of files that are compatible with other platforms outside Move4D. So each platforms, all the interoperability is not quite nice between the platforms. So even they are, most of them declare that are compatible with FBX or with USB. The reality is the way of creating the FBX. It's not the same for each platform. There are small details that we need to consider. So maybe tomorrow we will explain a bit more this, and we will talk about applications.
That sounds awesome. Have a good night. Thank you.
Okay. Thank you very much for your time. It has been a long training, but we will continue tomorrow.
Thank you very much.
Okay, thank you.
Thank
Bye.
you. Bye.
Thank you. Bye.
Okay. First of all, I would like to excuse Beatriz Mañas because she's not able to attend today. But in any case, he will be in contact with you if we want to continue organizing some future collaborations.
Good.
Okay, so the session for today, it's divided in 2 parts. First one is related to the data export, and then I will introduce you some information about applications of Move4D, just an overview of possibilities and projects that we are carrying out here at the IBB as summary of examples that can inspire you to work with Move4D. So first, Sofia will start with the data export applications.
Yes. So hello, good morning, everyone. And yes, I'm going to be in charge of the first part. So in this part, I think it will be shorter than 45 minutes. So it's better if we have time at the end of 2 sessions to talk about any doubts or questions that you will have. But of course, as yesterday we told you, please interrupt in case of need with no problem. So we're going to review which are the kind of formats that we are capable to export with the Move4D software. I don't know if you have been already using all of these, but I'm going to do an overview of each of the options that the software offers to have a big picture of everything. So as Anna explained yesterday, just a few slides, once you have your data, you can do the exportation from the data window. And you have the option of doing it from a project or from a subject. The idea of doing a batch of exportations from a project is that you can do with one in one process, you can export the, here I have an example. Yeah, all the subjects you want in all the captures you want. So you can leave it exporting during the night in case you have a lot of data, and you don't have to go subject by subject. So maybe you're familiar with this, but when you open the exportations window, you can select which subjects you want to export and also which captures. Here you will see a count that will change depending on your selections and also depending on which captures you have processed, because there are some files that will be generated without doing the processing, like for instance the PLY. This is not updated, sorry. I will, because here I will show you that now also there is an option of the exporting the S4D file. So the PLY and the S4D file, you don't need to process to export this. We will see that. And the rest of them are related to a homologous mesh to be active and being able to be created. So, well, yeah, here we have the example of just choosing one subject, and you don't have, of course, to choose the subjects because you already chose which one, and then here you will have your um your captures. This is important also because in this, when you are accessing from the project, here you will only see the captures that you define in your project protocol. Because sometimes it happens, it for sure will happen, that you define a protocol and you do the same with every subject, but sometimes you want to do a copy or anything in one single subject. So these special captures that are done for a single subject won't appear here. So here you will be able to export all the captures from the protocol, but in case you have some special cases for in different subjects, you have to come from here, from the subject. Okay, so let's review the types of formats that you can export. So the first of all is the PLY, which is the raw point cloud. We will see that, and maybe you already know, that there are some that will be generated one file per frame, and others that will be just one file for the whole sequence. In the case of the PLY, since we have a bunch of raw point clouds, we will, if I generate the PLY of a capture, I will get as many files as frames I have. So the number here just express the number of sequences, but then the files will multiply by by the number of frames. Okay, so the second file is the S4D. The S4D is the Move4D native file, and this is only one file for the whole capture. And we decided to include also this format because it may be the case that the software experiments some updates in the processing algorithms. So sometimes you have data that is processed, but then with a new version, you want to reprocess your data, but you don't want to overwrite your already processed data. So you can export your native files of the captures and then move to a different folder and then process with the new software, so you can even compare or anything you want and keep those data. Okay, so the next is the OBJ. I'm sure you already know about this because this is a standard in 3D format files, and this also is one per frame. And the OBJ that Move4D creates generates three different files. One is the OBJ, but will go the OBJ without the texture, like in gray, without color. And then it will also create a PNG file with the texture of the avatar. And then a third file, which is the MTIL file with the material settings for the renders of different softwares. Here, I wanted to say that this is really useful because sometimes you want to have anonymous avatar. So if you just remove the PNG from your folder, the files will be without texture, and this is considered an anonymous file, at least in the Spanish regulation. And also in one project, what we did is we wanted to remove just the face area, which is like the most identifiable part of the body, and we just create a mask in the texture, because since we have homology here, you always have the same parts of the body in the same part. So we just created a mask with the shape of the face, and we just removed the face from all the subjects, and we had like anonymous data to share with the client with according to the regulation. Okay, let's jump a few formats that I will come back later, and let's move to the FBX. The FBX is widely used by many softwares of animation, design, biomechanical, and so on. And here we have a whole set of options. But the idea of the FBX is that it includes the homologous mesh and together with the internal skeleton. So here we give several options because each software has its own particularities. So here we kind of cover a lot of the most common or used programs in animation and other applications. We kind of cover all of them doing a combination of the options we give. So the most simple one is the one file per frame. And here what we have is one file having the homologous mesh plus the skeleton. Here we don't have to compact any information because since we have one file per frame, we can structure the information the way we have it. But then there are many in general, all the programs that we can find that work with sequences of motion or animation, they normally work with one file per capture. So here we had to reorganize the information. I told that yesterday that the deformations of the mesh are compact to blend shapes. And the information is there anyway, but just we have to rearrange it. And here we have the option of put it in a single blend shape and multi-blend shape. Here the information is the same, but is the way it is structured. In general, most of the programs are more the way to have more compatibility is to have the multiple blend shape. The single blend shape, we introduced it because there is a software called OptiText that I don't know if you're familiar with, that is used for garment design, that was using the single blend shape. But in general, for instance, in Unreal, I don't know. Oh, no, they work. Here, there are some examples of some 3D script generated with the Move4D integrated in Unreal and Unity using this FBX one file per capture multi-blend shape. Okay, then we also have the option of including the skin animation or not. The skin animation is means the internal skeleton. You can include it or not. And but in general, it is interesting to include it because in many programs you can include your skeleton, and also you can do some refinements or change a little bit the posture or animate the way you want and so on. This gives you a lot of opportunities. And then if you include the skin animation, you have an additional option. If you want to include at the beginning of the sequence a virtual transition from the A pose to the recorded motion. This also was included because it was really interesting in the area, in the sector of garment design, because normally they start with the garment in 2D, with a mannequin or the person in the A pose, and then they transition to the sequence. So you can include this. And then we have a situation with the texture, because in this kind of format you cannot include all the textures from each frame, because Move4D, as you know, captures the texture of every single frame, but here we cannot include all of them. So here we give some options. First, you can put the A pose texture. That this sometimes we found it useful because when you capture with objects in around, sometimes they are printed in the texture because they are being seen by the modules. Like for instance, the bike, I can remove the points of the bike from the point cloud, but not from the texture. It will be some parts of the bikes impressed over the texture. So in these cases, if you just printed the texture from the A pose, can be useful. Or if not, another option is to choose the first frame or none. Okay. Okay, here's another example. This is a Cloud 3D virtual fashion software. Okay, so I again jump to the GLB because this is really related to the FBX. The GLB is an open source format. It's like the MPEG of the 3Ds, like the images, but in the 3Ds. And it is really similar to the FBX. It has more or less the same information, but it works with multi-blend shape option. Here, this is why we don't give the options here. And it is depending on if it is binary, it is GLB, GLB, sorry, or if it is in ASCII, is GLTF. And it works just like the FBX we included because it was also a format that was having like relevance, and is also compatible with a lot of softwares. Okay, so here we can see some examples of applications. Sandra will talk later about all the possibilities, but at the end, it is really important for us to be able to connect with other softwares for to have more value of creating our data. So here, I don't know if why they play here. We have some. This is something of the PowerPoint. Okay, now it's working. Here in Blender, we have an example, or here it's a virtual reality platform, or in a video game, or and so on. You have a lot of possibilities. Then, okay, let me add one more file concerning the 3D animation environments, which is the native file from Blender, and is the .blend, because Blender is compatible with a lot of formats, or FBX for sure. But as I told you, we cannot put inside the FBX all the texture of all the frames. But in the dot blend, you can put all the textures. So we also added this option in case you are really interested in having in Blender your capture with all the textures of every frame. So you can do it with this option. Okay. Okay, so here, sorry. Yeah, here there is just as a summary that we have some limitations of the containers of FBX and GLTF. Is just one texture per sequence, and that we had to rearrange the information, as I told you. It's not a direct transfer, but we have to do some arrangements, but they work. So this is not really a limitation. And yeah, in general, so the FBX is the most supported format, and in general, multi-blend shape generally is more compatible. Here, and also in the user's guide, we include a table with the compatibilities. And it is important to say that it is different to when you read a no than a dash, because sometimes you can import the data in a software and you can think that it is working, but it is not working as it should. So if it says yes, is that everything is structured and working well. Partial is that it has either some problems with the skeleton or with the blend shapes. When it says no, is that it doesn't read well none of them, and the dash is directly non-compatible. But we can see that there are a lot of platforms that are working well with the formats that we are created. At least this list has at least one option that will work fine. Okay, so and let's move to a different sector, which is the most related to mocap or biomechanical applications. And there is the option of creating a TRC. I'm sure you are familiar with this. So what you need to introduce is a CSV file where you, I don't know if you can see it here, you define a list of, but here I also have the file here. You define in the first column the names of the landmarks that you're interested with, and in the second column you have the ID number. The ID number, you can get it really easy from your 3D, because, well, I recommend to visualize it like here, and you can, with the right button, sorry, I don't know why it's not now. Okay, with the right button you can see here the number. So you can choose a set of landmarks that are interesting for your research or your project or whatever, and you can write them down here. And then what you get in the exportation is something like this, which is the landmarks that you ask for. They have like the coordinates in the three dimensions throughout all the frames. So you can then introduce them into some softwares of capture motion analysis, like the Mocha or the OpenSim or things like that. Then there is also the option of exporting the V8 format, which is created with the kinematic model of Vicon. You have all the description of this model in the user's guide, and it is normally used in programs like Xsense, OpenScene, in Vicon, programs that are of motion capture or motion analysis, but you have to be very careful because sometimes each software has their own way of defining the local coordinates. So this is something to take into account, to be careful with this. And the last thing I wanted to review is these two formats that I excluded because they are different. This is not about the 3D. This is about the measurement we can extract from the homologous meshes. Anna explained yesterday that you can see some static measurements once you generate the A pose, list of more than 100 measurements. And then another dynamic measurements in the dynamic tab. Anna already show you, but I can show you also. So when you have the A pose, you will have here. Sorry, because I'm in my laptop and this scale is not the best, but here you will have a list of measurement that will be created automatically when you generate the A pose. You can visualize them over the 3D. So in this with this option, what you can do is to generate the CSV, sorry, format from with all the information by frame, and also the dynamic measurements, which are here in the dynamic tab. You can also export them from here, and also now we are including in the next version an option of defining personalized dynamic measurements that after the Sandra session, if we have time, I wanted to introduce this new tool, which can be really interesting. And the way of exporting the values of these dynamic measurements will also be from this option here. So this is all from my part. So I leave the floor for Sandra. Of course, you have any question, here we are.
Thank you. I also ask a question for the TRC. When you right click and you get the I value, is that I value going to be the same for everybody? So we just have to do it once.
Yeah. So what you mean here? Sorry. Let me share again my screen.
For the homologous mesh. Yeah, that's fine.
You mean when you define an ID?
Yes.
Yeah, this is the meaning. This is the sense of the homology of the homologous mesh, is that we have anatomical correspondence. There is anyway a paper published about this correspondence, but yes, the nose tip is this value for my 3D mesh, and it has to be also with yours. So yes.
Okay, perfect. Thank you.
This can be very useful for some specific applications that can appear in the specific research projects that usually we are doing some new things that are not inside the commercial software. This structure of the data, it's interesting to program your own Python routines and to extract specific body metrics that can be useful for any assessment or any analysis that you can do. At least when with my presentation around different applications, you will see that depending on which is the objective, sometimes we need to measure some specific things in the body. And at this moment, there are not all the potential body metrics inside Move4D. For instance, in the new version, we are going to include also volumes of body parts, because the distribution of the IDs in the topology of the mesh are including some semantic lines that can separate automatically the arm or the legs or the thigh and the calf. So this can be useful to compute volumes of body parts of one specific person and volumes of the body part along the movement, because the volume can change during the movement. So for biomechanics and yeah, kinematic analysis, could be interesting to work with this kind of variables. Okay, do you have some more questions related to this section?
I have one. Is it possible for when like you are selecting the static measurements to select the specific ones that you would like to have, or does it export all of them?
I think you can you export all of them in the A-pose because they are all calculated automatically when you are computing. For the dynamic measurements, it's possible to select only the ones that you want to compute, and then to export, the exportation will only store the variables, the measurements that you have selected in the computation.
Muchas gracias.
Some more questions?
I don't think so. I think after we see your applications, we did pull together a few slides. So if there's time, we can show you some of the stuff that we're doing. If not, we can follow up after.
Okay, so I'm going to show just an overview of applications. I'm not going to go in deep, but yeah, maybe after my review, we can discuss about which are your potential applications now and which are the. Can you see my PowerPoint? Now?
Yes.
Okay. Okay. In our team, in the IBB, we are several research group, 5 research teams. One focus on anthropometry. This is our team when we have developed Move4D. There is another team that is specialized in biomechanics. Another team focus on digital health. Another focus on biomedical engineering. And the last one is focused on user experience. So there are most of the projects involve several research teams because all it's very connected. Especially the team focused on human factors. Yeah, they are doing many applications that requires digital human models to analyze the ergonomics of products or environment. So we have several connections there. But at the end, most of the applications or projects that we are doing with Move4D can be classified in 4 sectors. One more related to human factor or ergonomics, another related to biomechanics. We are working in several applications related to avatar animation in virtual reality or augmented reality, extended reality at the end. And yeah, and we have another sector or field of application that is related to the computer vision and the computer graphics. I mean the transition between the video and the 3D models and how to connect both. Move4D can be a tool to infer 3D body shapes from videos, from 2D to 3D. That it's what we call. In the case of human factors, most of our work in the past was done in anthropometric surveys to understand how the body shape and size varies across the population. So we work in doing anthropometric surveys in Spain, but also we work collaborating with other organizations in other countries to gather information in other places and to exchange data in order to have more information about the variability of the human shapes worldwide. And the application of the anthropometry, 3D body shapes, variability in the understanding better the fit in clothing, personal protective equipment or exoskeleton. At the end, wearables that are all the products that are wearing tight contact with the body, and at the end are wear when the person is performing an action or an activity. So how the anthropometry and the body shape varies with these activities is going to be important in the better understanding of the fit. And in ergonomics of environments, the workplace and the vehicle, the in-cabin ergonomics are two elements that are also important for the applications related to Move4D. In biomechanics, most of our activities are addressed to clinical applications. This is our main area of research, but sometimes we are also doing some projects related to export performance, biomechanics applied to export performance. So our experience is that these are the two big areas when the biomechanics are biomechanics related to movement analysis. It's more used. In avatar application, the creation of a human avatar, and especially the creation of a digital twin of an actor, an athlete, or a patient, these are three lines of creating a realistic avatar that can be introduced in a digital world. It can be a virtual reality experience to perform a treatment, or it can be a generation of contents for the metaverse, or a virtual reality environment to create a digital a film in a digital way. And finally, computer vision. Most of the computer advances or computer advance in what we can see today, it's more relying in the generation of data sets. So the creation of data sets, especially ones with a very high quality that can be done in a laboratory environment. And if we combine this kind of data sets with others done in the wild, these two assets or sources of information are really very important to advance in computer vision and computer graphics, creating new generative models and creating new agents. So I'm going to show some examples of human factors. This is one of the projects that we are running at this moment. It is an anthropometric survey of the European population of children. This project is led by, it's coordinated by the European Standardization Committee, and the IBB was selected to be the technical leader of the anthropometric campaign. This campaign includes two countries, Spain and Netherlands, just to cover south and north of Europe. And it's At this stage, when we started 3 years ago, it was in static postures, including the 4 postures that are included in the ISO standards. And for this purpose, we developed a portable version of Move4D. Now we have this system more optimized, and we can mantle and dismantle it in 2 hours. So this is something that we work in during this project. So now we are able to be more or less efficient doing this kind of surveys and measuring in many different measuring points across a country with the Move4D system. I want to mention that now we are we are planning a new survey for adults, and one of the things that we want to add is dynamic anthropometry, because only with static anthropometry is not possible to cover all the requirements that are needed to include specifications, thresholds, and reference values in the standards for the design of safety criteria in the standards related with different type of products. In the case of children's, mainly toys or environments in kindergartens, furniture, export facilities. But in the case of adults, we need to add also the manufacturing environments with factories, the workplace, the workstations design, and also the personal protective equipment. And this is something that applies to the factory and the workplace, but also in the we are seeing that for military applications, it's also applicable. And one of the projects that we did last year is related to the in-cabin design of the new air fighter, the European military airplane. And yeah, it's necessary to collect data from scanning data from the pilots. So we did a survey scanning pilots in different postures in order to have information, digital human models that can help the ergonomic design of the cabin. And this kind of ergonomics designs is going to be done using simulation tools and 3D environments. So it's also important to create the digital models with the internal skeleton that can be directly used in softwares like Ramsys or Blender, or even Unity or Unreal, that are environments that are more and more used not only for virtual reality, but also for ergonomic purposes. So with our experience generating this data set, we collected databases representing the different type of populations, adults, children, male, females, different age ranges, and we are using it for many applications, clothing, fitness, health, ergonomics of workplace, animation, personal protective equipment. And we need to do processing of the data in different, to organize and to obtain summaries of the data in different type of formats. We use anthropometric tables with statistic summaries. We use also bivariant plots when we want to establish a sizing system, analyzing the primary measurements in related to a product and the fit of this product in the body. And we used also digital mannequins that sometimes it's important to create different type of morphotypes representing different body proportions in order to use it as a reference in the design process, in order to check in a virtual way during the design process if we are going to accommodate properly different body types with our design. So this is an example in the case of osteoarthritis knee brace. The purpose was to optimize the design and the sizing of this brace. That's why we generated or we use different girths in the leg and distances between these girths to understand different morphotypes of the leg in the population. This is something that we did in static, and now we are starting to work with this kind of approach in dynamic. And that's why the dynamic measurements that we can obtain can help us to gather information about which is the deformation of the leg when we are wearing the knee brace, and the regulation and deformation capacity of the materials if they are in the range to accommodate these variations of anthropometry. This is another example with an exoskeleton for the workplace. In this case, it's important not only to consider the measurements, but also how the position of different anatomical points in the torso, especially in the hip area, the pieces and the axis and the pieces varies because the location of the actuators and the active sensors in the exoskeletons, in this type of exoskeleton, these sensors, active sensors, are going to transfer the load properly to the musculoskeletal chain in order to avoid the injuries in the parts that are more critical in the body, and to transfer the load to the parts that are more prepared to have loads. In this case, the hip. So the anthropometry in this case is not only a question of fitting the dimensions, the hip gears or the waist gears. It's important also to consider which are going to vary the locations of the supporting points in the hip. And the variability of these supporting points during the activities, working activities, will be also crucial. We are collaborating with several companies. In this case, it's an example of a project done with the French company Decathlon. This is they are specialized on sport equipment, different type of sport equipment, protections, wearables, clothing. And for them, it's very important to transfer all the fitting tests and design tests that they are doing with physical prototypes and with mock-ups to a digital environment. For this purpose, they need realistic mannequins based on real body shapes and based on real movements and based on the deformation of the movement of the body with real movements. That's why they collected a data set of humans with different body types, males and females, and they are developing a body model to control the shape of the body and the deformation of the soft tissue of the body with different export activities. This is a publication that they presented in 2 years ago in a conference. So you can see more information there. And related to how to avoid or reduce the number of physical fitting trials with live models and with physical prototypes, it's to use digital tools to create the patterns in clothing, and to use also realistic representations of the body in movement to test this kind of 3D patterns. So we did several projects, a couple of projects to compare design patterns designed in Cloth 3D with actual scans of the real garment using Move 3D, and comparing all this information in order to, at the end, design a set of a fitting test, a digital fitting test that will be a set of movements that can be performed with a new avatar that can be introduced in Cloth 3D that includes real body shape and real movement, and to compare if this kind of stress patterns are related with the fitting evaluations that are doing experts in a laboratory. We are trying to gather also insights, new insights of using Move 4D to improve the design of new products. And in this is an example of a project addressed to evaluate different design parameters of a diaper for early walkers. The different parameters of the diaper was the volume of the diaper to absorb and the liquids, and the pressure in the waist area. So it was created 3 prototypes combining these 2 design elements, and then we used the underwear condition as the reference to compare which diaper can reproduce a walking pattern more close to the underwear situation. So in this case, we use Move 4D as a motion analysis system with the babies to gather this kind of biomechanical parameters. We measured 20 children with these 4 conditions, and we use different biomechanical parameters to compare the 3 prototypes with the underwear condition. And then it was also possible to obtain digital human models of the baby in different postures that can be were used by the designers in order to optimize the pattern of the diaper using this kind of digital human model. This is something that it's new research. It's very costly because only the setting up the protocols to do this require some time, but at the end, it's new methodologies that are providing new insights for innovation in some products. Related to the ergonomics of the environments, they are also interesting the cones of view, the points of view, the fields of view that in combination with the different postures of the avatar inside the cabin. So in this case, we are using Blender because it's a free environment. You can program your own tools, and it's possible to develop add-ons to do several operations with the avatars in an automatic way. So some add-ons can help to include the cones and also to restrict the skeleton chain, so you can inside Blender, it's possible to change the posture of the avatars that are provided with Move4D. The problem is that Blender is not able to control the positions of the skeleton, considering the anatomical restrictions. So we have created our own add-ons to control this, to impose this kind of controls and to be more easy and user-friendly, the use of these avatars inside the Blender. This is an example that we can do with vehicles, and in this case with children. This was a work with furniture company in order to optimize the design and the regulations of the furniture for children that are in a range of ages that can vary a lot. And continue with the sitting postures, the car industry, it's for the car industry, it's very important the ergonomics inside the cabin and the ergonomics of the seat and the ergonomics inside the car. And the development of the autonomous car, it's introducing new requirements related to the postures of the humans inside the car. So only driving is not going to be the testing posture in the future. So we are doing advances and work in creating new postures and new movements that are going to be feasible inside the autonomous car. So we are using Move4D to capture different actions. In this case, we are stressing a lot the optimal use of Move4D because we need to do a setup of a mock-up of the driving car, trying to be very minimal, trying to be not very invasive. So we design a mock-up system with not many elements. That's the minimal ones that we need to control the posture with the wheel and the seat. But at the end, yeah, only the seat, if you see in this picture, it's hiding a lot the body. And if we remove the seat, we have big holes in the captures that we need to cover with our automatic processing software. So this is one of the situations more challenging for the system. And we did several pilots in order to check which is the better distribution or position of the mock-up and the seat inside the scanning volume in order to optimize the field of view of the Move4D modules and try to capture all the data that we can with optimizing the location of the subject inside the scanning volume. For instance, in the top view, we can see a distribution in the short axis of the scanning volume, then we can observe holes in this area of the torso. And if we are arranging the mock-up in the long axis, we can see that we are capturing much more data. And even if we design an elevated platform, we are capturing even more data, because at the end, the position of the sensors of Move4D are fixed in the top or in the bottom, and if the seat is in the bottom, we are missing possibilities of capture of one of the sensors. So this is something that is necessary. And then we also did some analysis, scanning with real seat, car seat, that it is super invasive. Also, we did scans with a minimal occlusive seat in order to obtain actual data, some actual data in the back. You can see here in this picture, in the back and in the bottom, because otherwise we can complete the information of the back and of the bottom with the automatic processing, but in this processing, we are not considering the deformation, the physical deformation, the physical interaction between the body and the seat, and the real and physical deformation of the soft tissue in the buttock and in the back done by the seat. So this is this kind of previous research or previous pilot testing that we are doing in order to establish the best way of capturing when we are using Move4D in a specific, very specific situation. This is an example of what we are obtaining at the end. This is processing done automatically in Move4D, removing the original capture, the segmenting person, removing the seat, and then the homologous mesh, and the homologous mesh with the internal skeleton. We did also a couple of projects related to cycling. One was related to the garment that should be very well fit to the body, but other was related with the aerodynamics of the bike and the aerodynamics of the posture of the athlete in the bike. So the good bikes and for professionals are like a plane. The developers are analyzing every detail, and even they are using fluent aerodynamics, finite element analysis with aerodynamics to simulate the air in the athlete in the bike. And for most of the professionals, the bike are designed in a customized way for them. So in this project, we scan cycling in different postures in order to generate the accurate digital human models of the athlete that can be used later on by another team specialized in finite element analysis to simulate the aerodynamics and to decide which are the best parameters in the design of the bike. In avatar animation, to generate, to do the processing in Move4D in an automatic way, is necessary to scan it with tight clothing. In animation, most of the artists are creating the avatars in two steps. First step is to generate character. And then second step is to dress it and animate it, because the character can be used in a virtual environment using different type of dressing or movement and in different conditions. So the character are usually created in naked conditions, and they use Marvelous Design to dress the avatar, and they can. The interesting point also with this software is that it's possible to define physical properties in the textiles in order to give this deformation of the textile according to the movement. And it depends if this is more a hard textile or a light thin one. They can move in a more fluent or way, or and yeah, with the movement. And then after the creation of the textile and dressing the avatar in Marvelous Design, it's possible to add textures, colors, and to put it in a virtual environment. So more or less, this is the pipeline of working with avatars coming from Move4D in virtual reality. And virtual reality now, animation, it's a sector that is using a lot of platforms. We have included some of them here: Blender, Maya, Fusion 360, Unity, Unreal, Omniverse, but there are others like Houdini or that are very, yeah, they use a lot of platforms. So the ecosystem of softwares that today is used in the production of digital content is super big. So that's why we included different formats and different options of the configuration of the formats to be compatible exporting the data to all these situations. In this, for this kind of applications, we are starting projects and ideas, concepts into fields of applications. One is related to language of science, sign language with the avatars, and how these sign language avatars can be connected with the chatbot, and how to do this in an automatic way from DLL with using DLL agents. So this is one of the projects that are starting now to conceptualize, and we're starting with small things, doing measurements with expert in sign language, and transferring this movement from this avatar to other avatars. And yeah, now we are also in collaboration with other teams, seeing how to connect this with chatbots or with something more automatic. And in the case of health, in the sector of health, we are testing the use of the avatars in mirror therapies for rehabilitation. Now, the mirror therapy has been validated as a very interesting tool to speed up or to accelerate the rehabilitation in several pathologies, and it's done using a collection of physical mirrors just to create a fake and to show the patients that they are performing the movements more advanced than the situation that they have now. For instance, in the case of a stroke, when we have a mid part of our body are affected and requires the rehabilitation. They have one side of the body that it's moving normally, and the other that requires this kind of rehabilitation and treatment. So if they can see during the rehabilitation the two parts of the body moving in a natural way, it's they are accelerating the recovery. And yeah, with the physical mirrors, what they are doing, it's a fake to do a symmetry of the part that they are moving properly to show that in the other part. No? So these are very these systems are not very sophisticated, so they are hard to use, and sometimes the patient cannot be seen very well using it, or they are not very friendly to use it in a practical way. So that's why to do this kind of approach in a virtual environment, it's more easy, but it's required to create first the digital avatar of the patient to introduce this kind of things. I'm going to go now to explain some elements, some examples of projects related to computer vision. This is a project that we started a couple of years ago, generating a data set of, we have almost 80 people, different body types, males, females, even different ethnicities. And we synchronize 4 RGB cameras with 4 point of views, different point of views in the laboratory. You can see the 4 point of views in the slide. And the cameras, the RGB cameras, are synchronized with the Move4D. So we are able to align the information of the homologous mesh processed with Move4D with the RGB camera, the pixels of the RGB camera. So this is a way of doing an automatic annotation of anatomical points of the body, a dense mesh of anatomical points of the body in each frame of the video in the 4 views. So we can do with here in this video, you can see the bright image. When you can see the person in the bright image, this is the avatar of Move4D, and the dark image, it's the RGB camera. So you can see, it's difficult to see the difference because the overlap between the video and the Move4D mesh, it's perfect. So the good point is that the anatomical annotation of the video is going to be very accurate. And if we have the dense projection in the video, we can also project the body parts in order to detect, to do an automatic segmentation in the video. And we can also annotate the joints or a sparse number of points. So this is a data set that we are using to train our own markerless system, because the end, with this markerless, we can have more accuracy in terms of anatomical location of joints and landmarks. Then we are able to, with this training, we are able to capture bodies with, or to infer 3D bodies or skeletons with 4 cameras. This will be more accurate, or even with only 1 camera. This is in an internal environment in the laboratory, but then it's possible we can use other models that are public or are in the state of the art, like MediaPipe, to gather information in more real situations, like in the factory or in the street or in an sport environment, to measure athletes, and then to use it to combine information from the lab and information in the wild. So this it's something that can be a potential combination to do more complex research. And one of the elements that I mentioned yesterday, it's there are some software, like in this case Unreal, that enables directly to train what they call the deformers. The deformers are individual plane shapes for a specific avatar that can be used to animate the avatar in this environment with more accuracy. So it's possible to use Move4D with a collection of movement, protocol of movements, in order to obtain these plane shapes, individual plane shapes, and to use it to include it, to introduce it, these new plane shapes in Unreal, to train these ML deformers, machine learning deformers, to be more realistic in the creation of avatars. Okay, regarding the biomechanics, I'm going to cover 4 possibilities. One is related to the combination of Move4D and OpenSim. In OpenSim, it's possible to compute inverse kinematic and to obtain forces. And yeah, the forces are related to the possibilities of injuries and the risk of injuries in some situations. So measuring athletes and different movements and using it in OpenSim to do this is something that can be interesting. The other studies that we are doing, it's more related to export equipment and how this equipment it's influencing the performance. So in this case, we are analyzing the compressive garment. Compressive garment are very are used in export to accelerate the recovery of the athlete, and yeah, to improve the performance in in some situations. The problem is that now there are not protocols, or there are not methods to quantify the effect of the compression garment, and there are not options to analyze which is the proper or the optimal fit of the compression garment to achieve the best performance. So we are using Move4D to analyze this quantifying data. So at this moment, we are working with several gears in the leg. One of them is in the calf, and we are doing the analysis into situations before doing an exercise and after 1 hour running, so in a fatigue condition. So we can see differences we can observe differences in the gears in fatigue and non-fatigue, between fatigue and non-fatigue conditions. And we are also analyzing the effect in the shape of the section of the calf, not only the measurement, but also the shape of the section. So we can observe more dispersion in the shape of this section in the leg. We are comparing here one leg with the compression garment and the other leg without the compression garment. So we can see more variability in the shape of the leg in the leg without the compression garment. And then we see that the shape of the leg change also. It's more rounded. So the compression garment, it's containing the soft tissue, and this effect of containing the soft tissue, it's more beneficial for the recovery. So it's this is something that we are piloting now. This is is in an exploration phase, but this is something that it's new compared to the typical analysis of compression garment. Sophia showed a way of using the TRC file to export the data of the virtual markers of the body, and it's possible to use these virtual garment markers in the traditional motion capture analysis system, creating the biomechanical model that is connected with the markers, and after this, to compute the joint angles of the different joints of the model. We have a link here to in the bottom part, you can see a publication that we did in Gait and Posture about the use of Move4D for biomechanics. In this case, we were focused on the gait analysis. The model is based on the lower limb. Since we can obtain shape of the body, it's possible to I don't know why the leg is not animated. Okay, we can see the deformation of a part of the body to quantify quantify the biomechanics in different pathologies, and to obtain some metrics that can be used to do a tracking or a control of the rehabilitation process. This is also published in a paper in Gait and Posture. And it's possible to observe only viewing with a view of the 3D mesh during a movement that the deformation, the surface of the body with Move4D is reproducing the activation of some muscles and the deformation of the soft tissue. So one of the ideas is, okay, the muscle activation is today nowadays measured with electromyography, EMG. This is a very complex signal in terms of preparation of the instrumentation process. We need to clean very well the surface, the skin. It depends on how well we are clean and where we are putting the sensors. If we have more or less fat in between the surface of the sensor and the muscles, we are going to have more or less noise or in the signals. Yeah, and then the signals requires a lot of post-processing from the electric acquisition to the signals that are reproducing the activation of the muscles. So there are a lot of propagated errors in between. So we are also analyzing how to measure the muscle activation with Move4D and how is the correlation with between these two techniques. This is something that is under research now in a PhD. And then finally, one of the first projects that we did with Move4D was related to the biomechanics of the breast and how to design a bra, an optimal bra for a sport practice, in particular for running. So traditional studies used a marker model in the breast to analyze the displacement of the breast in the 3 planes relative to the movement of the breast in the 3 planes relative to the movement of the torso. That's why they include these 3 additional markers in the shoulders, in the torso. And yeah, the objective is to compare and to analyze the effect of different design elements of the bra, and in particular difference between different type of bra, the compression bra, the encapsulation bra. The objective of the bra is to reduce or to minimize the forces in the breast related to the acceleration of the mass of the breast during the sport activity. And the approach of reducing this force is different in the compression bra, is to approximate the center of mass to the body and to the torso, and the effect of the encapsulation bra is to support from the bottom part of the breast, reducing the force of the gravity. And first thing that we did was to use the equivalent markers as IDs of the mesh in the homologous processing. So we can measure the same biomechanics without markers, and then we can obtain the same type of curves in the 3 planes in order to compare different type of routes, but we can also expand this analysis not only to for specific points. We can expand all this analysis to the full surface of the breast in movement. And this is a good option to innovate in the design of the bra, considering more possibilities in the design elements to optimize the support and the reduction of the forces. And that's more or less all from my side. So this is a quick overview of very different things, that just to inspire you about possibilities that you can do. Most of them are in a very early stage of research. So Move4D is a new tool. So there are a lot of work to do.
That's great. Do you want us to give you an overview of some of the stuff that we're doing, or what would be the best next step?
I think if you have information about what we are doing, if you can share with us, it will be very, very nice, because then we have a more clear idea in which areas we can collaborate and how we can help you in your daily work.
Okay. I'm not sure if Danielle told you, but as a high level overview, we do a lot of similar types of work, ranging from ergonomics to biomechanics to markerless motion capture to body shapes to clinical applications in sports as well. So in our new labs, we have obviously the Move4D system synchronized with like a bunch of force plates in the ground, synchronized with markerless motion capture and markered motion capture. So like Theia 3D and Vicon in that case. In our other labs, we have force plate treadmills. We're getting low dose CT scanners to measure like the lower limb, and dual high speed fluoroscopy to look at dynamic motion of bones. So we can measure outside shape using Move4D, but also some internal geometry. And then take all that data we also are getting like an immersive cylinder. So I'm not sure if you've heard of like Igloo Vision, but like a full immersive virtual reality simulator with a force plate, treadmill, and motion capture. So we can do similar things, creating virtual environments from our Move4D data or other things. We can run open sim analyses in like near real time to show people what muscles are active and those types of things. And then a lot of high compute power as well. So lots of different overlap in many different projects, but maybe I can also just share my screen from my laptop to, I'll log in to show a few things that we're doing. But if you have any questions, I'm sure Allison can answer them while I log in.
Yeah, that's incredible. Your laboratories are very complete, even with a CT scanner. So that's very impressive. So we are running a project now to gather information with Move4D and also with a CT scan. But we are collaborating with a hospital because we are not able to have this kind of technology here at the IBB. But yeah, we are also trying to combine internal and external anthropometry.
So maybe we can help you, because we have like also a DEXA scanner, so we can do DEXA, which I know some people like Michael Black's group have done to body shape. But we do have, like a low dose CT scanner. It can do the whole lower limb from hips to ankles at once, and it can move up and down. And then Allison's also, she trained at Queen's, so they had the dual fluoroscopy to look at 3D joint motion. That's kind of
one of the things that we are trying to deal with in this kind of application is how to approach the difference between the Move4D scan that it's in standing posture, and the CT scan or the DEXA scan that it's in lying posture. So, and with the deformation of the deformation in this of the body in this posture, especially with obese people that with a lot of soft tissue, the shape is going to vary a lot in the two conditions.
The low-dose CT scanner that we're getting is like weight bearing. So
Yeah, so
you
it's
stand in it.
Being number there.
For some reason, I can't log into Zoom. It's pretty normal. You have the meeting. I send them to the teams.
I might email it. You can email it for me, I can open it.
One more time. You guys have any questions to ask while I figure this out?
So did you start some projects with Move4D? Did you start capturing and working with the data?
A lot of piloting so far. We have some data that I can show. I think I should be able to get in here.
It's just the tape like slowly going.
Yeah, so I'll just show a few things that we've been working on. So to start, I know we mentioned that one of the big things that we're working on is we've been working with the Canadian Armed Forces for a while. One of the things that they've done is they've done a big Canadian Forces anthropometric survey. It's a bit older with about 4,000 soldiers, men and women. But that was older where they had to put markers on people to do these types of things. So one of the latest things is they've gotten a new static body scanner, I guess. So as one of our recent projects with them, before we measured any of their motion capture, we've done a lot of work using like in-lab things, but also XMs. So we'll measure a whole bunch of movements out in the field under their clothing and these types of things. But in our latest data collection, we did scan them semi-nude, but also using their tack vest and frag vest and then their backpack as well. So this is just one example. And Allison could probably speak to this better than me, but we wanted to see if we could create some of our own shape models of them. And some of the methods are probably similar. But we did some work to take a reference mesh and then to morph it into the different people, so that we could also have no correspondence between the different bodies and do these things. And we don't have a very big data set to start, so some of them look a little bit weird. But it's a good starting point for what we want to do with Move4D when they come into the lab as well. One of the things we wanted to take away was the fact that when you do these types of things too, their posture is not standardized always. So we did brought them into some gaming engines and standardized the posture and then smooth the meshes. So, but what we get from that, we ran PCA and also PLS to get some workable models, but then we get similar types of things where We then have shape models for the Canadian Armed Forces, at least the data that we collected that will grow. And then we can morph them between male versus female, different things like body shape, size, and so on. And we could also change certain parameters like chest girth, and then it will morph the bodies to match it as well. So we've done some work semi-nude, but also we can see how, if you scan them with their backpacks, how different things capture how the backpack fits on them as well, depending on their size and shape, because of some of their clothing would be the same. So we do want to continue to scan more and more soldiers, and we're having a lot of them come into our lab probably in September, because Canada is buying some new kit, and we need to look at fit and these types of things as well. So looking at body shape and fit of clothing and equipment, I know is tough, but it's something that Canada and some of our allies are interested in. So that's something we're taking on. And part of the reason why we wanted to get our own 4D body scanner, to also understand not just static shape and fit, but also how that changes dynamically as well.
So in this case, the equipped scans are also processed with an homologous mesh, so you are fitting a template, your template.
Yeah,
Yeah, exactly. That's it. You know, we just use like the coherent point drift to establish the correspondence between all the different meshes.
Okay, and the anatomical correspondency, it will be based on a sparse number of points, because with the dressed body, it's more difficult to know where is the anatomical points of the body. So you have the eyes, some points in the face, and maybe in the hands. I don't know.
It wasn't using any specific reference points, so it's just trying to match the whole mesh overall. But it probably would do better if you had also included specific points to mesh.
And which is the density of the topology of your mesh? Which is the number of vertex?
Good question. I don't remember. It's probably, I don't know, like 30,000 or something. I can't remember exactly what it is, but
yeah. We could as well, right? We could.
It's just to know if it's our mesh. It's around 50,000 points. It's to know it is in that level or it's more dense, because then to deform the maze to reproduce these detailed parts of the equipment, maybe it's necessary more density. I'm not sure, but that's why I'm asking.
Yeah, we can follow up after, and we can customize a lot of things, and we're going to get bigger data sets and probably scan them in the lab with Move4D plus a lot of other things. So we can also know their underlying skeleton using different biomechanical equipment or these types of things as well.
Okay.
I know we have 15 minutes, so I wanted to show a couple other things. Yesterday, Alex collected some data as well, but you'll see that we do have, now we have Move4D synchronized with, right now they're not rotated to the same coordinate systems, but we've been able to do that. So we have our force plates in the ground. You can see there's a bunch of them that can move around into different spots. So it's customizable in terms of if they're in a straight line for walking, or if we want to do cutting or something else, they can move into different positions. Our Vicon system itself has 10 optical motion capture cameras and then 8 video cameras. So with Move4D, we have all the RGB cameras and the motion capture camera synchronized. And so we've done a lot of work with Theia 3D, which is a markerless capture from Kingston, and we know them pretty well. But now what we can do is we have all our Move4D data, plus we can do markered biomechanics or markerless in those ways. And we've done some validation work before. We know that Theia 3D also tracks the underlying skeleton pretty well when you do have the armor and you do have a backpack. So it can still track those. And so we're not sure if that will be helpful if we have like their semi-nude mesh, their homologous mesh. We have homologous meshes with all their equipment on, but we can also understand what their underlying biomechanics are a little bit and then put them back together. So you can see that when they're doing different movements. Just did this earlier. Some legacy video.
It happens all the time.
It worked fine when I tried in my office an hour and a half ago. But...
Yeah, we did some tests with Theia and also with Capture. And I think we are working with Capture here at the IBB. I don't know if you had the opportunity to test both also, Capture and Theia.
No, we've only used it. Alice and I both did our PhDs at Queen's where it was developed. So we know the team from Theia pretty well. But their new version works well and it tracks like super well with the weapon, with the backpack, with the armor. So we've kind of been working with it and it has native integration with Vicon and also with Qualisys because we're replacing a lot of our cameras. So you can run Theia from directly within those as well and combine marker and markerless data. So it's been pretty useful, but now we have the opportunity to have all of these data synchronous to Move4D. We could do a lot of different validation. We spit Theia, we spit marker data. We can now put Move4D data into OpenSim for some validation type work as well. But we have them all in the same space and we'll use them in different ways. But it seems to be working. And Alex also did some of these non-homologous mesh things with some of the armor that we use, but it looks pretty good. We just have some work to do to start to better understand how to look at fit and these types of things dynamically, which I think is obviously one of the reasons why we wanted to chat with you. I'll show one last thing, maybe. So one of the things that Canada also wanted to do is they want to do some, one of the challenges when we do just this homologous semi-nude mesh is that we know that if we put a bunch of stuff on them, they don't move the same. So they're going to move slower, they're going to transition slower, they're going to do all of this type of stuff. So we can't just take their semi-nude movements and then dress them after because they're going to behave differently. So what Canada wanted to have is kind of a virtual software where we've measured a whole bunch of soldiers to look at how much they slow down or they move differently or they behave differently as a function of load worn, bulkiness, stiffness, those types of things. But we're working on kind of just consolidating some of that stuff within one software. But we can take our XSense data, for example, and merge it with different avatars. So we have to map the kinematics onto their bodies from our static body scans for now. And in the software, you can take off the helmet, the mask, their armor vest, their backpack, and it will pull different files different models we've generated that behave differently based on what they wore during that, or if it's a man versus a woman, or they're carrying more weight and so on. So we've kind of consolidated these, but some of the movement patterns don't directly match the scans. So we have to do some mapping. So again, 4D body scanning will know that the movements match the scan as well. We can kind of use those together, but it's kind of just showing a few different things that we're working on, but for all of them, it's similar, but we have good use cases for using the 4D body scanner to look at fit and movement and those things as well. Yeah. You guys have anything to add?
Okay, good. Yeah, that's very interesting. You have a process established from the scanner and the laboratory with all the synchronized systems. I think you have a very good laboratory to gather many information that will be, you will take advantage of all the data to generate many types of models, combining all the information from Theia, from force platforms, from the motion capture, and also with Move4D. So different levels of data combined are, yeah, sounds very good.
Awesome. So yeah, we just wanted to show you a little bit of some of this stuff that we've been doing as well, because maybe that will help as we have questions or you guys have thoughts around
And is the virtual environment developed by yourself, or it's Unity or something?
This is Unreal Engine. We have a full-time research engineer, but his expertise is in game development and design. So he's also played around with a lot of the new things like meta-tailor. I know you were talking about an Unreal Engine, what's that called? The ML Deformer. So he's done stuff like that, also with motion matching, which I know is something big in Unreal Engine now. So he's been able to take, we created kind of like statistical models of movement that behave slower if people weigh more weight and so on. And then he'll take the body scans and then map our movement from XNs or these types of things onto them. And then have them dressed and do these things and behave realistically. So this is part of a bigger project we're working with for the Canadian Armed Forces, but they want to do some of these virtual fit assessments, understand will people behave slower if they carry more weight. Even if they put on a thing, will it restrict their range of motion? There are just a bunch of different questions for why we wanted to get a 4D body scanner as part of like our bigger set of labs as well. That makes sense. Yeah.
Okay, yeah, it's very interesting that you're very advanced on this.
On some things, but
yeah, I think it's good to have a specific application that is for defense, for the soldiers, protective equipment, and to run all the possibilities from end to end, focus on one application. So that's very good.
Awesome. I know a few of our students in this room are interested in looking at static fit or dynamic fit. And I know that a lot of the new militaries are procuring new armor, new backpacks, new different things, and they want some way to, user trials are super expensive, as you all know. So we will test a subset of people from Canada, maybe the Netherlands and some other places in our lab with different kit, but looking at methods to understand, you know, the fit of these pieces of equipment on top of their homologous semi-nude scan, or if we could ever add additional templates or those types of things. These are all thoughts that we have for next work or potential collaborations or these things as well. But we just want to.
We would like to run similar projects here in Europe, and in fact, I was in contact with or following the work done by Alan Caffey and Hein Dannen in the NATO, in the specific group related to 3D body scanning technologies. So yeah, that it could be. At this moment, I think this group stopped their activity, but I think it could be run Move4D, an opportunity of collaborating from different NATO countries in not reinventing the same things in all the places, but yeah, taking advantage of a collaborative platform or something like that.
For sure. And there is a NATO Digital Twins group now. We presented at that conference in Orlando in early December, maybe. So I know a lot of people are interested in these types of things, and we've been talking to, well, before all of this latest stuff happened, we were talking a lot to the US, but now a little to, we're talking with I have a meeting with the Netherlands tomorrow for some of this stuff, and they'd like to come to our lab while we do some of the Canadian testing as well. But perhaps there's something bigger we can do with NATO, but also in the short term with us optimizing use of 4D move.
Okay.
Yeah. Great. I think it's almost 12, but we just want to thank you for all the training, and we just want to give you a bit of an overview so you understand a bit more of where we're coming from, and then hopefully we can have some debrief and perhaps another discussion at some point soon, whenever you're ready.
Yes, sure. I think we should maintain the contact to see possibilities of collaborating. One of the elements that we discussed also yesterday was the possibility to provide the sequence of meshes in your topology. I'm not sure if this can be useful for you, so we can first step can be if we can share the topology and the internal skeleton of your mesh, just to see how far it's from our current one, and and see the feasibility of doing this kind of plugin to convert. And this is a very collaboration that is very focused on the use of Move4D, but maybe in a research project we can also discuss about other options.
Yeah, that sounds great. And we can adjust like the mesh we generate or add different skeleton to it before if it makes that transition easier. But yeah, it's something for sure we'd like to do, to maybe be able to generate these meshes automatically with a different template or something. That would be super useful. But that sounds awesome. Yeah.
Perfect. So thank you very much for all the team to attend to this today's training. So yeah, we just to remind that we have a support service, or you can contact directly to the link and phones provided by Daniel. That is usually the point of contact, and if the question is more related to R&D, they can deliver to us the questions, and if more related to technical issues with the scanners, he can, he and his team can solve the situation. So take advantage of this, because we are super open to be in touch and to know how is your experience using Move4D and how we can improve the use of the system, because we need to know, to have feedback from the users in order to improve the functionalities and what we can do with the system. And of course, feel free to contact me, or if you have a direct idea of a project or an R&D issue, we are open.
Awesome.
Okay.
Yeah, thank you for your time, and I'm sure we will be in touch soon. Yeah.
Thank you to all of you.
Thank you.
Bye.
Thank you. Nice to meet you. Bye.
Bye.
Bye.